Good morning. So I'm pleased to be introducing the Noether Lecture today. The Association for Women in Mathematics established the Emmy Noether Lectures in 1980 to honor women who have made fundamental and sustained contributions to the mathematical sciences. This year's speaker is Birgit Speh. Dr. Speh received her PhD from MIT in 1977 under the supervision of Bert Kosten. She held postdoctoral positions at the University of Chicago and the University of Wuppertal before joining the faculty at Cornell in 1980. In 1983, she became the first woman to earn tenure at the Cornell University Department of Mathematics. That was especially exciting for me because I was a young graduate student there at the time, and we were all very excited to hear that. Dr. Speh is known for her work on representation theory of reductive Lie groups and its relationship to automorphic forms and the cohomology of arithmetic groups. In her thesis, she classified the unitary representations of low-dimensional general linear groups and then introduced, in her early work, a special class of unitary representations of the general linear groups over the real numbers that now bear her name. Speh's research over the years has explored connections between unitary representations, automorphic forms, and the geometry of locally symmetric spaces. In recent work, Speh has studied restrictions of representations of reductive groups to non-compact reductive subgroups. This work on symmetry breaking has led, in joint work with Kobayashi, to proofs of conjectures of Gross-Prasad for some pairs of orthogonal groups. Speh has made outstanding research contributions for over 40 years, and yet looks exactly the same as she did when I was at Cornell. And she's been the recipient of many honors and awards. We are pleased that she has agreed to be this year's Noether Lecturer. She will be speaking today on branching laws for representations of non-compact orthogonal group. Please join me in welcoming Dr. Speh.
Thank you very much for the introduction and for allowing me to give this Noether Lecture. So when I was preparing for this lecture, I started to think about impact of Noether on what I'm doing. And well, when I was a child until around age 14, 15, I was dead set of becoming a veterinarian in a zoo. That seemed just the most exciting thing in the world to do. Then around that time, I started looking at the public library, and there were books about elementary particles. And, well, elementary particles seemed like the next great thing to do to understand the world. So my zoo ideas and veterinarian ideas disappeared. And at around the same time, some substitute teacher in the school gave me a book about calculus, and that seemed to be nice too. And so ultimately, I decided to major in math and physics, always with the goal, more or less, to understand physics and the world. So, in being in physics, my first encounter with Noether's work was in a course on theoretical mechanics. It's a course people, if they are physics majors, still have to take. And so there, something called Noether's theorem shows up, and the Wikipedia version, in short, is if a physical system has a continuous symmetry property, then there are corresponding branching laws. And that's how it's often taught. And so, okay, what is a continuous symmetry property? Well, as an example, rotational symmetry corresponds to the preservation of angular momentum. And in most courses, it's never completely clear what really the continuous symmetry all entails. So, in preparing, I looked at Noether's original article. So, I think it may not be completely clear on the screen, but there are several interesting points here. One is It's almost 100 years ago that she proved this thing. And still, I mean, it's one of the fundamentals of physics. So we always think of her as a mathematician, but in fact, her contributions to physics have been fundamental. Another part I found interesting is her article actually talks about Lie groups very explicitly. Is that she uses Lie groups to prove her work. There were other examples where people could do things, but the fundamental part of her work is Lie groups. That's the novelty of this article, that she very explicitly classified and describes what she means with continuous symmetries. A third point, which is very weird or surprising, is that she was actually not born as Emmy Noether, or her birth certificate is Amalia Emmy Noether. And she, when publishing, started changing her name to Emmy. It seemed like better than Amalia. So, using the language which is actually even contained in this article, our previous example would be phrased as, if the action of a physical system is invariant under the group SO3 of 3 cross 3 orthogonal matrices, then the angular momentum of the physical system is preserved. This is pretty much the formulation she gives as an example in her paper. So, here is a picture of Emmy Noether at around the time when she proved this fundamental theorem. So she was a nice young society lady, and she was interested in fundamentally in physics and in new physics, and in fact she was interested in Lie theory and actions here. So my next physics course was quantum mechanics, and there Lie groups again show up in even a first course, namely every course has the example of the hydrogen atom, and essentially even every chemistry course in some version, and essentially you classify the finite dimensional representations of the Lie algebra SO3, which is a 3 cross 3 symmetric matrices, and you look at their restriction, and you look at the restriction to the smaller group SO2, and that's basically used to determine the energy levels and the states of the hydrogen atom. Okay, so at that point, I realized that to do physics, I had to learn Lie theory. Still, how all of this was completely related wasn't all 100% clear, but it was clear that one needed to learn this. And then came quantum field theory. And here, infinite dimensional representations of non-compact Lie groups are extremely important. And so the Lie group, which is of importance there, is the group SO31, which is a group which preserves the quadratic form x squared, y squared plus c squared minus t squared. It's a non-compact group of 4 connected components, and depending where in the literature you look, it's either the connected component which you're interested in, or one of the subgroups here of index 2. So that's also the group of general relativity, and so it's extremely important in quantum field theory, and in fact, it's also one of the groups which is explicitly discussed in Noether's original article, and it discusses what really the physics laws are and the invariants which are preserved. Okay, so At that point, if I really wanted to understand quantum field theory and the whole classification of elementary particles, I needed to learn infinite dimensional representations of Lie groups. No choice. It was necessary. So I started to learn some of this, and basically I never returned to the world of physics after that. I stayed interested in infinite dimensional representations of Lie groups, and this was the time when the Lagrange theory came out, and so there was a ton of interesting things about representations of Lie groups. So that's how I got in this field and what really the big impact of Noether's theorems was on getting me set on this particular road. Okay, so what I want to talk today is in restrictions of infinite dimensional representations of the Lorentz group, or in fact, more generally, of the group SON1 to non-compact subgroups. And the subgroup I'm interested in is just the orthogonal group, which is one dimension smaller. Okay, so the first part is sort of like before when I talked about quantum mechanics, we look at the compact picture and see what happens there. So let's start with the compact group ON1 and its finite dimensional representations and their restrictions. So ON1 is the set of all orthogonal matrices which preserve the definite quadratic form. So it's just orthogonal matrices whose inverse is equal to its transpose. So this group is compact and has two connected components, namely the orthogonal matrices of determinant 1 and -1, and we usually look only at the component, the special orthogonal group, which is just the identity component. Okay, so a representation is simply a homomorphism of a Lie group G into a continuous group GLN of a vector space where we take a finite dimensional vector space here. So the classical results, which go back to the 1920s, give a complete classification of all such representations. And they're parameterized by a sequence of integers which satisfy with a decreasing sequence, and dependent if n is even or odd, the last integer is allowed to be negative or not. For if n is even, the last integer is allowed to be negative, otherwise it's not. All other integers are positive. So that was one of the big accomplishments of Cartan and Weil. This all goes back to exactly the same time as Noether's original article. And she actually even mentioned both the work of Cartan and Weil in her original article. Okay, so I refer to this sequence as the weight of the representation. Often it's referred to as highest weight, but I will use the word weight in this context. And, well, if I look at ON, it's the group is disconnected, so our representations have additional feature, namely they have a signature, which is plus or minus, or plus minus, which means when we induce the representation of the group of the group SON to ON, the representation stays irreducible. It doesn't break into two pieces, and So there is nothing special, no signature. Examples of this which show up for many people is O2 is a commutative group which is isomorphic to R modulo C, and the representations are all one-dimensional. And from Fourier analysis, you know that they are simply the complex periodic valued functions. T goes to e to 2 pi I and t, and they are parameterized by integers n. Positive or negative. This is exactly one of those cases where n is even, and, well, we have just one integer, so it's allowed to go from plus to minus. If we go to SO3, we have the representations are parameterized by a non-negative integer. And the trivial representation of ON corresponds to the weight 0, 0, everything 0, and it has signature plus. If we go to the non-trivial one-dimensional representation, then it has a signature minus, and, well, there is nothing with signature plus minus. It has either signature plus or signature minus. Okay, and again, this is a very classical problem which was studied shortly in the 30s, basically. And so what the result was, we know that if I'm restricting a representation of the orthogonal group to an orthogonal group of one dimension of n minus 1, it's a direct sum. There are multiplicities, namely constants, in front of the representations which appear as a representation of On. Oops, as a representation of n minus 1, this is a typo. And we call this multiplicity, this function's number m with what it appears in the restriction as the multiplicity. And so to understand the multiplicity, one way of thinking of it is simply thinking of it as the dimension of the space of homomorphisms which are SON minus 1 equivariant into another representation. That's just another way of thinking of the whole thing, and it works nicely. It's all, everything is an irreducible, direct sum of irreducible representations, and so the world is in fine order. And the classical branching rules refer basically to an algorithm of how to determine this multiplicity if we know the representations of the smaller group, representations of the larger group, and, well, we parameterize them by weights. So what you do here is you get a rule of how do these different weights behave, and it's really an interlacing pattern. So I'm just writing this out for in one case, namely representations of the odd crew SO to the even SO, and this goes back to the 30s. The multiplicity is 1 if we have a very nice, the nicest possible interlacing pattern between the weights of these representations. Otherwise, it's 0. Okay, so, of course, this is exactly the theorem of, in which people use in quantum mechanics and hydrogen atom. And so there, we take a representation of weight 3, restricted to representations of SO2, and we see this is the only last piece of this interlacing property, just the last inequality of the interlacing pattern, which is left over. Okay, now let's look at the non-compact group. In this case, what we had was we had a symmetry group of a quadratic form of signature n1. We have 4 connected components, and again, SO is this group of matrices with determinant 1. It's disconnected, and it has index 2 in the full group ON, comma 1. So we encountered this group when I was talking about a little bit about groups in quantum field theory. This, if we take n equals 3, is the Lorentz group. And so this was one of the groups which was in fact explicitly mentioned in the article by Noether. Now, if we look at finite dimensional representations of the Lorentz group or the special orthogonal group of signature n plus 1, 1, and they are very similar, same rules as if we take the group SO n plus 1. They are classified by highest weights or by weights. They have an additional thing, they have the signature, as we saw by going from SON to SON. There's a little plus minus signature there, but otherwise it's the same. And so the branching laws pretty much go over exactly the same interlacing properties of the weights. And we again have a little bit of a problem. There's an additional technical thing which has to do with basically the signature, because things have matching right there. Okay, so I wanted to talk about infinite dimensional representations. The first thing is we need to know a tiny bit about those representations. So here, a lot of what I'm talking about is vague. I do not want to go into any technicalities, so I'm trying to, nothing will be absolutely and completely correct in many ways around here. So the definition of a representation of the non-compact semi-simple Lie group on a topological vector space is a group homomorphism into the continuous invertible linear maps of V to V, and there's an additional technical condition. Before, in the finite dimensional case, I also mentioned the word continuous, but it didn't mean much. Here, it means an awful lot, and that's where all the technicalities come in, because we have a topological vector space, and we have the homomorphisms of the topological vector space to itself, which again have some topology, and if I talk about continuous, I mean continuous between those topologies. So that's a little bit of the exact background of what this definition is. Okay, it's irreducible if there is no closed subspace which is invariant under G. And what we're interested in, obviously, is irreducible representations. And there, the really bad news is that almost all irreducible representations of the special orthogonal group n plus 1, 1 are infinite dimensional. That's good news or bad news. For people like me, it's good news, but for a lot of people, it's bad news. And the good news is that most of these irreducible representations are, in fact, induced from a subgroup. and for a finite dimensional representation of the subgroup. So you can handle them. So what I want to consider here is, well, let's take an infinite dimensional representation and do what we did before when we restricted. So, okay, let's restrict it to a non-compact subgroup. What we should get is, well, we get a representation of a non-compact group, and there is an obvious problem if you want to decompose such a thing into irreducible representations, so it's a large technical issue of what you do. So in generality, this problem is probably unsolvable if you just take an arbitrary non-compact group and restrict it to a non-compact group. But what we will see is for SO and 1, we can in fact get very similar rules to the finite dimensional representations if we make all definitions completely correct and look at the right subset. Okay, so this is the precise case. What I would like to do is look at the restriction of infinite dimensional representation of the non-compact group SON plus 1, 1 to the non-compact group SON 1, just as a test case where this is the easiest possible test case if you want to ever look at restrictions in general and try to understand what they are. And this slide should be, according to what I'm talking today about, is restricting some infinite dimensional representations. Because one can do the whole general case, but I won't do the case here. Okay, so the first obstacle to all of this is if I take one of these infinite dimensional representations and I restrict it, it is not a direct sum. The nice part about the case which I discussed in the finite dimensional case is, oh, everything is a direct sum. It's a direct sum of irreducible representations. There are multiplicities which are naturally defined. So, okay, we know what everything is and can work there. This is simply not the case here in the infinite dimensional case. But we can still try to sort of recover by looking at the finite dimensional case and see how we can learn from there and from some results in automorphic forms. Namely, the definition of the multiplicity we can use, which we had in the finite dimensional case. I sort of showed that the multiplicity is nothing else but the set of equivariant operators, H or SON1, 1, equivariant operators between the representations. So that definition makes sense, and obviously everything inside here is to be continuous. So what we need to know is we need to know the operators. We have a representation of the large group on a space V, a representation of the smaller group on a space W, and we need to know the continuous homomorphisms between the two vector spaces, which are H equivariant, or equivariant for the smaller group. That definition makes sense. And so the intuition behind all of this is obviously that what you want is, you have no subrepresentations and no nice way of decomposing it, but you may at least be able to look at quotients. And so this way, what one does is we look at all the quotients. And we check, well, okay, how many different ways can I find quotients of my large representations which are equivalent to a given representation of the small group? So we get still information about the restriction. It's not quite as explicit as it was before when we were in a finite dimensional case, but you can get a lot of information out of looking at this definition of multiplicity. Okay. So before explaining how to go on and how to get branching laws, we really need a little bit more about the infinite dimensional representations. So here things get extremely sketchy. So I mentioned before that most irreducible representations of the special orthogonal groups SON, 1 are induced from finite dimensional representation of a subgroup. So what I will, in this lecture, I will concentrate only on those representations which are not induced. If you take the other ones in joint work with Toshi Kobayashi, we could do those too, but it's a completely different story with completely different formulas. So what I'm looking here is, we are looking here at the representations which are not induced. So, for example, the finite dimensional representations are not induced. So those are in this list of representations. So each of those representations, we can assign parameters, which we call zeta parameters. And, well, we have a weight again. Same conditions as before, where we were with the finite dimensional ones. We have a signature, as we saw for the finite dimensional case. The signatures are either plus or plus minus. And the additional new feature is height. So we also define a height of a representation. And, well, the representations which we knew before, the finite dimensional ones, have height 0, and then it goes up, and only up to n to the sort of particular middle dimension. After that, if we would go past that, it would be sort of a repetition. Okay, so the trivial representation in this parametrization has again weight 0, 0, 0. It has a signature plus, and the non-trivial one-dimensional representation is also weight 0, 0, 0, and it has a signature minus. So if G is even dimensional, then unfortunately there is one case. If G is even, 1, then there's one case, namely the representation of height M have signature plus minus, and everything else has either signature plus or signature minus. And this problem does not show up if we are in the case of SO odd 1. So this one thing about signature plus minus is just a remnant from, or an important case, but it comes up because it comes up for particular even or odd signatures per cases. Okay. So the branching rules of those representations, which I just described, the irreducible non-induced representations. And so what we want is, again, we would like to have a rule which, for the branching, for the restriction, which shows us, well, okay, what is the multiplicity our representations are parameterized by weight, height, and signature. So what we would get is really a rule which involves all of these three quantities. And what makes life considerably easier is that the multiplicity is 1 or 0. So what it means in this case, we need to know when sufficient, necessary and sufficient rules, when is this dimension, this multiplicity vanishing. That simplifies life a lot, because if there would be additional constants, it would make life considerably harder. Okay, so what I'm writing out here is the theorem, which in this case, we take representations of SON odd, comma 1, and we restrict them to SO odd, comma 1, and we restrict them to an SO even, comma 1. So we have again our parameters, nu and mu for the representations, our weights. And what I'm assuming here in this is, if I'm starting with n odd, then the nu has a last parameter 0. The last weight of the parameter is 0. That's an additional condition, so it doesn't mean we look at all representations. And we get multiplicity 1 if both representations have the same signature, where same signature is, if I have a signature plus minus for one representation, then it means it has signature plus and it has signature minus. So if I'm talking about the same signature, I may talk about, okay, one group, one representation has signature plus, and the other one has signature plus minus, because signature is not specified. So that's what I call the same signature here. And for the height, what we have is, well, we can look at the height of the representation of the large group, the height of the representation and of the large group minus 1. Those are the only cases we can do. If the heights differ too much, nothing happens. And we have an interlacing pattern. And the interlacing pattern is exactly the same as we had when we looked at the finite dimensional representations in this case. So the only really new one here, feature here, is the case we have the height. The height really determines what happens. This is not the case if you work with finite dimensional ones. There is another version of this, which is the odd even case, and we restrict to SO and odd, but it looks again, it's the same scheme of things. So if you recall the finite dimensional case, I claimed the representations all have height 0. So our theorem here really is exactly the same as it would be for height 0, okay? The representation of the large group has height 0, is finite dimensional. The representation of the small group has height 0, that's the only choice. And we get exactly the branching law, which I stated in the compact case. There's a little bit of the signature, but that goes into that case as well. So If we look at examples for SO31, in that case, we can have a weight with two integers. So let's take just the easiest case where we have 0, 0 and signature plus. There are two representations, one infinite dimensional one with that weight, a finite dimensional one with this weight. If we want to see what happens, what possible quotients show up, we have to look at the interlacing property. That means, okay, the representations of the smaller group which possibly can show up, all of parameter 0. And so, in that case, we have just, again, two representations, one infinite dimensional one, one finite dimensional one for this. The infinite dimensional one in this case is a case where we have signature plus minus. And so our branching laws can be represented here as, okay, we have the representations of the larger group, which is a capital pi, the representations of the smaller group, the little pi, and if I have a non-zero multiplicity, it means I have a homomorphisms, and this homomorphism is indicated here by a red arrow. So those are the branching laws in this easiest and first case. Now, a couple of remarks. This branching laws for these infinite dimensional representations of the orthogonal group were originally just for a particular subset. They were suggested by and conjectured by Gross and Brassard. The representations, in their case, they wanted to have, since they came from number theories, they wanted to have a uniform theory which works for periodic and real groups and complex groups, all the same. So they are quite complicatedly phrased. And in our case, if you trace back what we do, is the representations which Gross-Brassard discuss are exactly the representations of the largest height. For us, they have, the height is in the middle, how we define our height. So they are about as far away from finite dimensional representations as possible in height. And in that case, our branching laws here really coincide with the branching laws which they suggested and conjectured in that case. And so, again, just these little interlacing properties between weights is what comes down, what their whole conjectures come down to. Okay. Now, if you start thinking of this, what do we have here, the laws, the branching laws? We have the ones for degree 0, for height 0, which go back 90 years. And we have the branching laws conjectured by Gross-Brassard for the representation with the largest possible height. And what we get is a very nice interpolation between those two branching laws. They really are exactly interpolating what these two branching laws tell, between the one on the highest and the one on the lowest. So, there is some hopes that by understanding all of this here very precisely, that you can easily make, or you can try to make some conjectures, again, in the cases of the indefinite orthogonal groups by interpolating, in general, the representations which are the highest possible height, whatever that may be, and the representations with the lowest height, and that this is a very general pattern, what you want to do. So, of course, your families of representations which you deal with, you have to define very specifically. In those cases, they will not be all non-induced representations. There will be a subset of that. But it's quite possible that you can find a nice branching law for interpolating, again, cross-Bresser conjectures with the old and well-known finite dimensional cases. And there are some special cases where you can, in fact, all of this is nicely worked out, but only in very low dimensional cases does this make sense. And your interlacing properties will be more complicated. It doesn't mean here they were nice, because I had my weight for the large representation, I had my weight for the small representations, and the interlacing properties immediately sort of showed that only finitely many representations of the smaller group can appear as quotients of the representations of the larger group. This is absolutely not the case in general. The interlacing properties which show up in all the computed examples are more complicated. There are many ways how you can interlace your weights. If you have decreasing sequences of integers, there are lots of ways how this could possibly be. And for each one of those orthogonal groups, these interlacing properties are going to be quite different, as examples show. But as far as examples show, it always comes down to various interlacing properties between what we call weights. And then, of course, you have the different heights, and so there's more to be done, but at least there's a hope that for certain families of representations, everything looks similar to the finite dimensional case. Okay? And so, thank you.
We probably have time for one or two questions, but first let me present Dr. Speh with a appreciation plaque for
Thank
the
you.
lecture. She really brought us from the beginning with Noether. That was marvelous, through interesting current work in the representations. So do we have maybe time for one question? Sure. Okay, well, let's thank Dr. Speh again.